So welcome to another December Liftoff webinar presented by Bond Technologies along with Lyft. My name is Joe Steele. I'm the Director of Communications and Legislative Affairs with Lyft. Thank you very much for taking the time to join us today. This is our final webinar of 2020. So thank you for joining us throughout the year. Hope that everyone is safe and well as we round up 2020 and head into what we hope to be a much different and much better 2021. Hope everyone is safe and healthy out there. A few housekeeping notes before we get started. This webinar is being recorded, so if you can be sure to put your phones or computers on mute, that'd be fantastic. Would avoid any background noise for the presentation. It will also be posted on our website at lift.technology over in the news and events section. So you can check it there in a couple of days, and you can share it with folks who who you think may be interested or may not have been able to join us today. I do want to take a couple of minutes before we get into talking about friction stir welding and technology and applications around it. I want to take a couple of minutes and share with you about Lyft for those who may not know who we are and what we do. Lyft is one of now 16 National Manufacturing Innovation Institutes. We are headquartered in Detroit in the historic Corktown neighborhood. And we are where manufacturing technology and talent matter. We understand that smarter manufacturing, the idea of connecting materials, processes, systems, and talent, that is going to drive advanced manufacturing forward in this country, and that is our mission as an institute. We know that on a global scale, the next area, the next region that conquers that will be the next economic powerhouse, and we want to make sure that that is right here in the United States of America. I mentioned that we are one of the 16 National Manufacturing Innovation Institutes. We were founded back in 2014 through the Department of Defense, and we are headquartered, as I mentioned, down in the Corktown area. We are a public-private partnership between industry, academia, and government, and a membership-based organization. We have members all over the country. Bond is one of our most active members. In fact, Bond was one of the companies that first stepped up when we brought the University of Michigan's rocketry team to the forefront to offer them some, to seek some assistance, some help as they are entering competition to launch into space next year. And Bond was one of the companies that first stepped up to help them. So we have a very active ecosystem. And we're proud to have Bond as a member. So what do we do as an institute? We are working to solve the manufacturing equation each and every day. So we do that, again, through connecting the materials, the processes, systems, and talent to drive American manufacturing into the future. We do that really through two programs at our institute. We have our our technology program first, that is leading innovations for tomorrow. And we have our talent program, which is learning innovations for tomorrow. We understand that we need to take these innovations from concept to commercialization, so we get them into the marketplace and into the hands of the warfighter as soon as possible. We also know that having the innovations there without the talent to be able to use them, without the people with the right skills, knowledge, and abilities to use them, doesn't make sense either. So we're trying to tackle both, make sure that we have the talent sector married with the technology sector. So both of those programs are really what make up our institute. I mentioned we are a public-private partnership and a membership-based organization. Through that, we have a number of benefits that we provide. This is really the core of what we do in both the talent and the technology programs. We are a trusted advisor. You know, I mentioned we have an ecosystem across the country of experts in industry, academia, government, in-house experts. We're not trying to sell anybody anything specific. We are Switzerland, as our CEO likes to say. We like to try to provide the best solution that will help our members' needs. We are a talent developer. We're developing new venues, new tools, and new teaching techniques to make sure that the advanced manufacturing talent base is robust and able to work with these innovations as they come into the marketplace. We're a convener. That is why everyone is here today on this webinar. So thank you for convening with us. Again, with our network of industry, academia, and government, we have experts in smarter manufacturing across the country and bring them together in various venues throughout the year. We are a technology showcase. If you have not been to our facility in Detroit, we encourage you to do so when it is safe to do so. We really showcase the art of the possible and bringing, seeing how we can, the benefits of connecting materials, processes, systems, and talent. While the pandemic is going on, I encourage you to log on to our website at lift.technology, take our virtual tour. You can click around and see our facility, see all the machinery that is there and the capabilities that we have. It is a showcase and a sandbox. We are not only showcasing the smarter manufacturing future, but we are also a place where folks can prototype, they can test, they can work on their innovations. So encourage you to visit us in Detroit when you get a chance. We are a connector. Again, public-private partnership between government, industry, and academia, really connecting the ideas, needs, and people to the right organization to move the needle. And finally, a technology accelerator, where we are moving emerging technologies from advanced concepts to commercialization to get them into the hands of industry and the warfighter. So leading innovations for tomorrow, our technology program really focuses on four pillars, from the digital to our history and materials research. You can see that through these 4 pillars, we are connecting materials, processes, and systems. A little bit deeper dive here. You can learn a little bit more about these on our website, or you can certainly reach out to us and ask any questions you might have. But really, again, connecting the physical to the digital as we're moving towards a smarter manufacturing future. The talent program, Learning Innovations for Tomorrow, has 4 basic pillars as well. It all kind of starts with our Ignite Mastering Manufacturing curriculum that we developed. We teach that each and every day at the LIFT Learning Lab, where we had pre-pandemic, we had 150 students a day going through there to really, learn about advanced manufacturing, learn about material science, and really expose them to the world of advanced manufacturing. We also offer world-class certification programs for the mature student, folks that may need to learn a new skill, folks that may need to upskill to gain their next position in advanced manufacturing. And finally, Operation Next is a program that is evolving as we speak. This was originally launched as a pilot down in Fort Campbell, Kentucky, to provide an opportunity for our servicemen and women as they leave the service. We wanted to provide them opportunity to gain credentials in advanced manufacturing careers. So we offered them that 6 months before they left the service. Our goal was 101 down there. We knocked that out, and now we're expanding it across the country. We just announced last week that the program is becoming available to the National Guard and Reserve here in Michigan and their spouses. So we're excited about having that opportunity. We're looking to announce a few more expansions, as well as the Department of Defense is funding that expansion to 9 additional bases across the country over the next couple of years. So we really think it's important to give back to our service members. Also, Operation Next is growing into industry. We're helping small and medium-sized manufacturers, kind of recover from the pandemic and provide training for employees there. So we're starting that off with folks here in the Detroit area, as well as in Pittsburgh. So again, more information available on that on our website. And again, more detail on each of those programs here. But that is about LIFT. You can certainly follow us on LinkedIn. You can follow us on Twitter. You can reach us the old-fashioned way via the telephone or on our website. Thanks again for joining us. I'm here for any questions. If you do have questions throughout the presentation, you can use the Zoom chat function and send those questions directly to me, Joe Steele, the moderator or administrator. I'm not sure exactly, or the host. I'm not sure exactly what my title is on there. I've done so many of these, I lost track of my title. But you can certainly send questions my way, and we'll facilitate the Q&A at the end of the session. So, without further ado, I will hand the program over to Dave Hofferbert, the president of Bond Technologies, to talk to us a little bit more about his innovations and applications around friction stir welding. Dave, I'm going to stop my share so you can share your screen.
Thanks, Joe. I appreciate the opportunity to do this, and I'm grateful to LIFT for all of the webinars that you've done so far. And we're happy to be wrapping up this series for this year. I'm also grateful to all the attendees. Looks like we've got a lot of people on here. I will say as just yet another plug for Lyft, what this organization does is to foster collaboration and communication. And there is a saying that the rising tide floats all boats. We really believe that at Bond. And so one of the components of what we do as a company is to educate, collaborate, and promote friction stir welding technology. And that not only benefits us, but it benefits industry in general and the markets we serve. So hopefully you get something out of this today that helps you. I work at Bond Technologies. I'll tell you a little bit about my company, and at the end there will be some contact information. I'm going to caution you that this is not intended to be a sales pitch. It would be great if we could work together in the future, but really it is not about sales. It's about promoting the technology and trying to give you a window into where we see the technology going. We're a small company in Elkhart, Indiana. We primarily build friction stir welding machines. That's our main source of revenue. But since inception, this technology has been migrating from the research world into the production world. Many of our customers in the manufacturing sector know very little about friction stir welding. So by its very nature, education is a component of what we do, and that includes process development, migration from the lab into a production environment, and all of the other technologies that are associated with that are also related to designing and building machines for friction stir welding. So this is an awfully curious way to join materials. When I first got into this, I looked at some of the examples of it and scratched my head and said, gosh, does this really work? Well, it turns out it does. And because I see from the participant list that there's quite a range of people on this webinar. Some of you may know a lot about friction stir welding. Some of you maybe not so much. So I thought it would be worthwhile to go through a fairly brief introduction to the technology. And then I'm going to spend most of the time focusing on applications and try to extract some of the interesting aspects of each of these applications so that you can learn what other people are doing, what's been done before today, and then what direction we see this technology going in the future. So the basics, we're using frictional heat with this tool shown in blue to cause material to plasticize. So picture a milling machine, a vertical mill with this tool in it that consists of a pin and a shoulder. So in step one, the spindle starts rotating. In step two, the pin, which protrudes below, plunges into the material. And in this case, we have two, say they're aluminum plates butted together. And as the pin contacts the material, frictional heat causes it to plasticize, and the pin plunges into the material. As the shoulder engages, it's a much larger surface, so the torque goes up, the amount of heat being generated goes up significantly, and the region around this pin tool becomes plastic. Now it's below the melt point of the material, so picture toothpaste, if you will. It's about that level of flow stress and shear strength. As soon as the region below the pin is preheated, the pin traverses along the joint. And there's a fairly complex motion that occurs during this traverse, consisting of both a fairly aggressive forging force in the downward direction, a mixing in the horizontal direction to stir these materials side to side, but then there's also a significant vertical component to the mixing that causes a high level of grain refinement in the material, as well as a strong joint. Some of the key attributes are that this is a numerically controlled process, so it lends itself to integration and automation. Because it uses frictional heat, There are not a lot of fumes or smoke. No filler is used. The only consumable is really the pin tool as it wears over the life of the tool. And I'll say there's no special joint preparation, but I have to caution that the joints do need to be abutted together fairly well so that there aren't large gaps. And in the event of certain welds, oxidation can be an issue. And so the removal of oxidation can occasionally be done. But as opposed to melt phase, arc welding, for example, the oxides become stirred into the material as opposed to inhibiting the weld process. You can join a wide variety of alloys, although the predominant application for friction stir welding has been and will probably continue to be aluminum. The skill level of the operator once the process is developed and put into production is fairly low, so it does lend itself to production applications in manufacturing environments. The basics of the process are shown here. To the left is a cross section of a piece of material that's being joined. You can see the weld nugget. That is the area of the most aggressive mixing and stirring. The thermomechanical affected zone is just outside that. The heat affected zone is a little larger than those two, but typically significantly smaller than the heat affected zone that's experienced with arc welding or melt phase welding technologies. The thing to note too is that if it's aluminum, for example, the temper is relieved to a T0 essentially because of the heating effect typically. To the right, we're showing some of the key parameters that are involved in the process. The forge force is pushing down on the joint as it stirs. There's a rotational speed, there's a traverse speed. So speeds and feeds, much like metal cutting. The tool has a pin and a shoulder. And there's an advancing side and a retreating side, which is notable. So if you jump back to the picture on the lower left, you'll see a little bit of a tail on the advancing side. So it is not a perfectly symmetrical weld nugget. So the process parameters start with the pin tool geometry, and then rotational speed and traverse speed and pin tool force are the three parameters that really affect the elevation of temperature, which then affects the flow stress of the material and results in the mixing of the material. This little graph shows the spindle speed on the horizontal with the feed rate or traversing speed on the vertical. And this is a kind of a useful graph to show what some of the areas outside of the ideal process window will look like and what the result is. So part of the exercise in productionizing this process is similar to many other processes where an experimental design is typically used to define the process window and the operating point within that process window. One of the key aspects of friction stir welding is the use of forge force. You can do this in position control. In other words, plunging into the material, getting shoulder engagement, and traversing along the joint with a constant position. But if there's any variation in the material thickness or the tooling, it can result in a variation in the engagement of the shoulder. This will affect the weld process. Therefore, the most common method of doing friction stir welding is to use force control, whereby the force is measured and controlled through closed loop control system in order to maintain a constant force, which causes the position to vary. So you'll see a couple examples in the picture up above. The top one is force control, the bottom one is position control. If you look at these graphs, the maroon or dark red lines show position control weld where the pin depth is controlled at a constant level. And you can see that as the tool welds over an intentionally created variation in height, the force varies. In the lower graph with force control, the pin depth varies as the force is held constant. which is a more desirable outcome. This results in a more consistent weld nugget and more consistent, more reliable material properties. So to do friction stir welding, it is advisable to use force control and use load sensors to be able to measure and close that loop. All kinds of materials, I should say all kinds, many kinds of materials, mostly metals, are welded with friction stir welding. But as I said before, it's typically used for aluminum. But there are dissimilar materials that can be joined. Aluminum 2000 series to 7000 series, for example, or aluminum to copper, aluminum to magnesium. I'll show you an example of aluminum to steel. Steel welding can be done. Even people, the rumor has it, have welded chocolate together. I'd like to see that sometime. Joint geometries are shown in this slide that are kind of popular. Some joints work better than others, but one of the things to be careful of is because of the high forge force and the high level of plasticity of the material, when a joint geometry is chosen, there needs to be very good support underneath. Let's take a look, for example, at joint J, which is a kind of a T-section. If the weld nugget were too large, you could imagine plasticized material causing a loss of containment underneath the flat horizontal plate. So in an example like this, one would use tooling to support that inside corner to avoid the plasticized material extruding down and out. The tool that does the work, this little guy has a lot of characteristics and is actually somewhat complex because of the fact that it's not only forging the material down, but also inducing a horizontal and a vertical component. So this big picture is of a conventional tool. It's a one-piece tool, so the pin and the shoulder are all made of the same material. Typically, these are tool steels, starting with something like H13 and going up to some high nickel cobalt alloys like MP159 or Nimonic series of materials. But the pin tool takes a lot of abuse, and so it has to be made of a very good material in order to last a long, long time. Not only are some tools fixed pin, but there's some variations on the pin tool design. The fixed pin is shown to the left. These can actually come in a one-piece or a two-piece configuration. We make tools that have the pin as a separate component with a backing screw so that you can actually change the pin length depending on the material thickness. The pins shown in the middle have two pieces, but the pin axis and the shoulder axis are actually separate. One of the benefits you can get from this is when you finish a weld, the pin can gradually retract over the last several millimeters of the weld to eliminate the exit hole that may be present with a fixed pin. The downside is that it does require an additional axis, and the equipment cost can go up, and it's a little specialized. But if you have an additional axis, you can also do the pin configuration on the right, which is an adjustable self-reacting pin. One of the big benefits of this pin geometry is that the forge force is reacted not by the tooling that supports the part as much as it is by that opposing shoulder. So for launch vehicles, for example, welding a large barrel where it's very difficult or complex to introduce an internal mandrel, this has found its way into welding tanks for rocket ships. This chart shows some typical aluminum alloys and the joint efficiency, which is really the ratio of the stir welded joint to the parent metal. And you'll notice that the 5083 O temper really doesn't lose much ultimate tensile strength after welding because it starts at an O temper, it winds up at an O temper. Others, like the 2000 series materials, have quite a range. And 6061 T6, which is a very common friction stir welding aluminum alloy, has a joint efficiency of around 67% or so. This chart compares stress strain curves for fusion welding and friction stir welding for the base metal. This is, in this example, it's a 7000 series T7351 material. But in most cases, like 7075, a stir welded joint does have superior joint strength to a fusion welded joint. In fatigue, friction stir welding also demonstrates superior performance to other welding methods. So the benefit from an application perspective is that you can, if the welded joint is the weakest link in the structure, friction stir welding gives you the ability to reduce the thickness of the material, and it allows you to lightweight the product. This has found its way into all kinds of industries. Some have been around since the early days of friction stir welding. Some are emerging. So I'm going to go into a number of examples and comment on how stir welding has impacted these particular applications. But first, I want to give you just kind of an insight from Bond's perspective, the kind of inquiries we are receiving, just to kind of give you a feel of what activity is going on. This technology is still migrating from the research and development world into the production world. So there's a tremendous amount of R&D activity that is still occurring in universities, national labs, and also in private industry. So if you look at automotive and R&D, for example, that constitutes about half of the inquiries that we currently receive. Here's an example of a launch vehicle application. In this case, it's a linear seam weld used to make a tank. This machine is at Marshall Space Flight Center making tanks. To the left, you see the ortho grid or iso grid. They do both in tank sections. So this takes segments and turns them into barrels. Once you have a barrel, you can weld barrel to barrel or barrel to dome with a circumferential weld. And this is a great application for that self-reacting tool that does not require an internal manual, although this machine does have a 18-foot diameter umbrella, essentially, that expands to support the weld so that they can also do conventional welding. This shows the construction of a dome using a Gore weld process, also for launch vehicles. One of the things I will say about the rocket ship people is that they realized early on that because aluminum lithium alloys have a great strength to weight ratio, they're great candidates to make rockets out of, but they are also very difficult to weld using conventional methods. So they discovered that friction stir welding was a really good applicable technology for making rocket ship tanks. And as a result of that, a tremendous amount of innovation and R&D has occurred by NASA, SpaceX, Boeing, ULA, and the folks that are actively involved, as well as overseas, the ESA, European Space Agency, and others have broadly adopted friction stir welding. One of the early adopters was Eclipse Aviation for the construction of fuselages without rivets, basically. If you get on an airplane these days, there's a lot of rivets on an airplane. Interestingly enough, in the airplane side of the aerospace industry, it's very difficult to change a manufacturing process to adopt a new technology. So where you see friction stir welding finding its way into the airplane business is on new designs primarily. Shipbuilding was another early adopter. The ability to join extrusions together to form ship decks is a very common application. One of the challenges is in the management of the straightness of these, because if the stir weld gets off joint, you're going to have a very weak structure. So keeping these straight, clamping them properly, and then tracking the seam to follow properly are some of the technologies that were developed in order to address long panel extrusions, including the shipbuilding industry. Steel has also been done. One of the challenges with steel that is actually seeing some traction now is the development of a robust pin tool that can live for a long time in steel. It's a pretty tough environment. Typically, the tools that are used for welding steel are a polycubic crystalline boron nitride, PCBN, or some of the tungsten alloys, tungsten rhenium or lanthanated tungsten. Pretty expensive stuff, and so minimizing the wear characteristics of those tools is an area of continued development in the welding of steel with friction stir. High-speed rail cars are typically made of hollow extrusions for the body structure, and so this machine happens to be in China making high-speed rail cars in an AB format. So it's a 56-meter long machine. They load one car while they're welding the other, and then they move the gantry down and weld the first one back and forth. You can use robots for friction stir welding, and for thinner gauge materials, it's a suitable application. Robots are basically a commodity. You can buy them, and they're treated as a component. So you put a spindle on a robot, you can do friction stir welding. However, even with the advent of deflection compensation at each joint, robots still struggle to be stiff enough dynamically. Statically, you can compensate if you're going in a straight line, but there are challenges in getting a robot to be stiff enough. So there are applications in production where robots are used with a FSW spindle, but it's primarily for thinner gauge materials. This is an interesting application that uses a multi-axis machine for complex contours. One of the challenges of complex contours is finding a path that manages the force and accommodates variability in machine deflection as it goes through the weld path. But this application allowed the manufacturer of this snowmobile to reduce the weight, reduce the center of gravity, and increase the reliability of the component that they welded. So they looked at friction stir welding as not just a cost savings and a substitute for a traditional method, but an opportunity to improve their product design. I think this is a cool application. It's a contactor for a power transmission manufacturer. And a couple of interesting things about this. One is that it did use a retractable pin to avoid an extraction defect in the weld. But the other is that one of the quality control metrics for assuring that the weld was done properly is the measurement of the resistance across the weld joint in micro ohms. This is a segment that is growing rapidly. Automotive electronics is including both battery trays as well as power control modules. Typically, it's a box with a cover. The cover seals a chamber that has coolant going through it to cool off the electronics. But there are many, many applications of this that are emerging in automotive. Another interesting automotive application is a great example of design for manufacturability. These links are welded together symmetrically, and it's an extrusion, so it's long, and then they're sliced to form suspension links. So they're sliced like bologna into short sections. Honda did some friction stir welding of the front K-member on the Honda Accord to join aluminum to steel. One of the things that happens when you join aluminum to steel is that intermetallic compounds can be formed. You may be scratching your head thinking, wait a minute, you said that the melt point isn't reached when you do friction stir welding, and yet the melt point of aluminum and the melt point of iron are drastically different. So what happens here is that the aluminum gets pretty hot, and the steel is really receiving a much smaller fraction of the heat input from the standpoint of where the tool is positioned. So the pin tool is mostly on the aluminum side. But what happens is you do get these intermetallic compounds if the temperature is elevated too much. And these are fairly large molecules. They can be pretty brittle. So the way that Honda achieved success with this application, and the way others are achieving success with the joining of aluminum to steel, is to seek a cold region or colder region of the process window to keep the overall temperatures low and inhibit the formation of the intermetallic compounds. If the electric vehicles are a skateboard configuration, as shown here, battery trays are a great candidate for friction stir welding. One of the benefits of stir welding for battery trays is the replacement of other joining technologies for the covers, like gluing and screwing, or using gaskets and bolts. So it reduces weight, improves the reliability, and so there's a number of benefits, and we're seeing the electric and the hybrid vehicle market become very active in friction stir welding. So it's an exciting segment to be a part of. Another growth opportunity for friction stir welding is a variant called refill spot welding, or friction stir refill spot welding. This is a process that can be used to either replace conventional resistance spot welding for aluminum or self-piercing rivets. There are 4 steps to the process. One is that picture, if you will, a shoulder and a pin or a probe. So they're concentric rings, and on the outside of those is a clamping ring. So in initial contact, the clamping ring, the probe, and the shoulder are all flush with the surface of the part. The clamping ring is not rotating, but the shoulder and the probe are rotating. And the first thing that happens is that the shoulder descends into the material to cause a lap joint to be welded, while the pin retracts vertically to absorb that displaced material. Then essentially in the refill step, they trade places, and what you're left with, shown in the picture of the weld, is a lap joint that has a flush top surface. So here's a little demo of how this works. The clamp ring comes down, the shoulder and the probe make contact, the shoulder goes into the part, the probe comes up, the probe goes down, the shoulder comes up, and then it removes itself. All this happens, it's already competitive with resistance spot welding and self-piercing rivets. As I said before, there's a lot of activity going on in the R&D world, and what's exciting for us is to be able to participate with some of our research partners and then migrate these developing technologies into the production environment where it actually benefits companies and helps the economy. So I want to talk about some of the trends, things that are emerging from R&D and going into the production world. There's continued activity with dissimilar alloys and high strength materials as the pin tools for steel and high temperature alloys get better. Applications for friction stir welding of steels and others become more and more prevalent. Metal matrix composites are being developed. Aluminum to steel, as I mentioned. Aluminum to magnesium is another opportunity. So there's a lot going on in the materials world, both the materials being joined as well as the materials that comprise the pin tools that are doing the work. As machines find their way into production, it's important to improve productivity through smart design of tooling, reducing cycle time. On the right, you'll see a tool holder that is instrumented for measuring temperature. One of the ways to improve productivity is, at least to improve the development cycle, to find a process window that works for a given application, is to measure temperature of the pin tool as it's doing the weld. We also have the ability to close the loop and control to a constant temperature. And that can provide some great benefits in certain applications. The machine on the left is used for long panel extrusion. One of the benefits of this machine is that it allows the next extrusion to be welded, to be loaded and put in place. So it's ready to drop in once the first joint is done. So in other words, prior to this machine, the way you would weld long panel extrusions is to load up 2 extrusions, butt them together, clamp them, and then do the weld. Once they're done, unclamp, index them out, load the next extrusion, line it up, clamp it, and then begin the next weld. In this particular application, historically, setup time was enormous. The setup time to actual weld time was many multiples. And so what we've been able to do with this machine, and I think this is a trend, is to develop material handling technology that allows the welder to stay busy most of the time. So this is a long panel extrusion example, but there are other examples in other industries. Many folks, and going back to automotive, want to do one-piece flow or rapid changeovers. So designing tooling that can handle the forces of friction stir welding and clamp the parts appropriately and yet be able to be changed in and out very quickly is an important area of development. We do believe that a lot of the technology that is going to benefit industry in the future with friction stir welding has to do with controls. In-process quality is a very important aspect of friction stir welding. The machines that we build and the machines that people use in general for friction stir welding gather gobs of data. The forces, the torques, the positions, the depth of the tool, all are important parameters and all lend themselves to process control. So there's the traditional statistical process control that can be implemented, such as looking at the forge force to ensure that it maintains some established range within the process window. Looking at the depth of the tool to make sure that the tool doesn't plunge too deeply for some reason or another. The classical gathering of data and establishing boundaries for warnings and alarms is a more traditional but still very important part of making FSW successful in production. Broken tool detection is another example. If you break a tool, you'll see you'll see a spike in the force, and you'll see a dramatic reduction in the traverse force. So there's ways to determine whether you've broken a tool or not. Just a side note on the design of pin tools, it is very important to strive to design a tool so that it fails by wear instead of catastrophically by breaking. And so by designing tools that fail gradually through wearing out, it allows us to define what that process window looks like over the life of the tool, and when that process window changes enough to where the weld does not meet requirements, then you can establish a tool life. Tool life is a very application specific thing, but it's important to know because that is the one consumable in the process. So certainly broken tool detection is important to avoid catastrophic failure and generating bad parts, but detecting tool wear and monitoring it is also important. Some of the work that's been done in academia and in the R&D labs has to do with frequency domain analysis as well. Turns out that if you can gather data quickly enough, you can monitor the traverse force and the cross-seam force as a function of pin tool angle as it rotates. And what you'll find is that there's a characteristic of that resultant force vector that shows you that you're making a good weld or not making a good weld. So I'm oversimplifying it a lot, and some folks have done fast Fourier transforms and neural networks and applying AI to be able to do machine learning that determines whether you're making a good weld or not. but that is an area that we predict will see a significant amount of advancements. So the control system on a typical friction stir welder is going to do nothing but get smarter and smarter in the years to come. So that's an exciting area to watch for us and to be able to participate in. I've run through a lot of stuff here. I did want to allow some time for questions, and so I appreciate everybody staying on board, and I'm open for questions. There's my contact information.
Awesome. Thank you very much, Dave. And now everyone can see why Bond Technologies is right at home at Lift. I mean, I can't even begin to describe that this is a perfect presentation that connected, and it shows the connection between materials, processes, and systems. And they're touching on the digital side at the end, which is where we are moving towards as an institute. So thank you very much. Thank you very much for that. That was great. Again, if you do have questions, please direct them to me via the Zoom chat function. I encourage everyone to reach out to Dave and the folks over at Bond. You see his contact information there. You can shoot him an email, give him a call, and follow up afterwards and see how their operation over there in Elkhart might be able to help you move forward. So Dave, we did have a couple of questions come in for you. I mean, the bottom line is, this is a great technology, as you explained, a lot of different applications and a lot of different materials involved. At the end of the day, how does this technology help, lower costs, say vehicles, for example? How does it drive lower cost? And there's also a side question about weight. How does this process really translate into cost reduction and weight reduction?
Okay, I'm going to use the example of a power electronics enclosure because that's one of the more popular applications that's beginning to emerge in the automotive sector. One of the common ways of making this power electronic enclosure with a cooling chamber is to put a plate on top of a cavity that has an inlet and an outlet port on it, and put a gasket around it and put a row of bolts around it. And if you look at many hybrid and electric vehicles, you'll find examples of that. It's expensive to put a gasket in there, machine the groove for the gasket, drill and tap a bunch of holes, and install a bunch of bolts. So friction stir welding allows you to make a loop around that part with a stir weld, form a hermetic seal, and basically you've reduced the parts count, you've reduced the weight, and you've reduced the cost.
Very good. Now, if I'm not involved in this process, if I'm new to the process, how do I become involved aside from working directly with you?
Typically, well, the answer is going to be work directly with us. All right, because
I think that's the best answer, right?
I can't tell you how many times somebody will come along and they'll say, "Hey, I've got this part, and I read in the welding journal about friction stir welding, and I've got this part. Can you use friction stir welding on this?" And so the first thing that happens is a dialogue about product design. Gee, you've got a great part here. Yes, it's a candidate, but it would be really nice if you could support it better over here, or you've got a lot of extra material over there that can be removed. So the first thing that we do typically is take a look at the design and try to make some suggestions for manufacturability. And then the next thing is to make some prototype parts, do some process development, and demonstrate by example that friction stir welding can work. Once that's done, then you can actually, once you've got a couple parts that you've welded, you can make a guess at what your consumable cost is going to be with regard to pin tools, what the tooling cost is going to be, and then more importantly, that lets us do a cycle time evaluation and say, okay, here's what your timing is going to be. How does this fit into the manufacturing process? And so sometimes The stir welding might be the long pole in the tent, and so maybe you need two friction stir welders to keep up with the rest of the process. But most often, that's not the case. So, and then there's questions about, do you want to automatically load it with a robot or have an operator manually load and unload the parts? But the first step is to take an example of an application and use it as a kind of a straw man to see whether the technology is suitable or not. Beyond that, there are companies like Bond and others that can do training and classes. We're not the only ones that will go on site and actually do formal training, and we'll scale the training to meet your needs. The Welding Institute, the folks that invented it, frankly, do a lot of that, and they're a great resource. And there's others too that can actually come on site and train people. And it's our objective not to cling jealously to all this knowledge. We'd like to have every customer that we deal with develop a competency in friction stir welding. So there's a couple benefits. One is that they master the process, they get better at it, and then they lower their cost to do it. And then the other is that they're not constantly bugging us for help, and they're on their own. So
Right.
So that's kind of our goal, to have people become self-sufficient and develop core competencies in it, and we can assist along the way in doing that.
Well, you hit on a couple of things there. The first is, TWI is also a partner of Lyft. So plug for our ecosystem, for you for being a member, for TWI for being a member. This is why we exist, to kind of bring, these experts from around the country and around the world, really, together to move the needle in advanced manufacturing. You talked a little bit about the going back to the design and going back to my presentation at the beginning about Lyft and the focus that we have on the digital side, particularly around ICME, the computational materials engineering, where we're taking a look at the materials in the digital world to make sure, see how they react to a different processing method. So yeah, a lot of stuff does go back to that design. If you get it right in the design phase, you'll be that much further ahead of the game. Couple other questions came in. Can you just real quickly talk about the limits or weaknesses of this technology? I mean, you talked about a lot about the benefits. Are there weaknesses there or limits?
Yeah, there are, and it's important to be aware of those. Not everything is a candidate for friction stir welding. I wouldn't advise you to try to friction stir weld a water tower together, for example. One of the limits is the need for strong tooling. The forces that are generated by this process can be pretty high. Picture, well, one of our applications, the forge force is 18 to 20 kilonewtons. That's about the amount of force of the weight of two SUVs pushing down on a tool that's about 1 inch in diameter. So the forces are really high. So what that means is that the tooling has to be able to support those forces, and the part has to be able to withstand them. So there's cases where you may not be able to design a part that lends itself to friction stir welding. Further, there are size limits. We currently have a job in-house that we're working on for the containment of nuclear waste that is going into a copper vessel that is 2 inches thick, or 50 millimeters. So we're welding 2-inch thick copper in a single pass with friction stir. You can't go a whole lot bigger than that without some serious challenges. So yeah, there are some limitations.
All right, excellent. I saw, did see our friends from TWI are actually listening in on this webinar. So great to see the ecosystem connecting. That was unplanned. So fantastic. Hey, one more question. I want to be respectful of folks' times. We have a few minutes left. Do you want to do your weld to the final heat treated state of an alloy, or prior to that and then heat treat afterwards to get the proper temper?
When you weld, you'll wind up relieving the temper to a T0, typically in aluminum. And so if you do want a certain temper, that needs to be done afterward. But also keep in mind from a materials property standpoint that there's a significant amount of grain refinement, which does change the material properties within the weld zone. So those things need to be taken into consideration. There is an international standard, ISO 25239, that describes bend tests, tensile tests, and other ways to define the material requirements. But that's an important thing to know going into the development of this process, is what are the material properties that are desired when you come out of it, and how do you test to ensure that you've met those? So relating the process itself to product performance is an important exercise.
Well, listen, I appreciate the presentation. I appreciate, we appreciate your membership. I appreciate everyone joining today. If you do have further questions, want to reach out to Dave, please do so. His contact information is up on the screen. You can shoot him an email or give him a call. As I mentioned, this is the final liftoff webinar for 2020. I want to thank everyone for participating. Again, you can follow Lift on our social media channels. Reach out to us with any questions, and stay tuned to your emails for additional webinars as we kick things off up in 2021. So, wish everyone happy holiday season, happy New Year, and we will speak to you in 2021. So, thank you very much again, Dave, and thank you everyone for joining today.
Thank you.